Thank you.
Okay. Yeah, thank you for the kind introduction. Actually, it's a very long title, and it can be a little, it can look complicated, but in the end, it's going to be mostly about rhombohedral multilayer graphene, different aspects of rhombohedral multilayer graphene that is going to be presented in three different parts. Here, RNG stands for rhombohedral n-layer graphene, and it's going to be about the notion of pseudospin magnetism and topological phases. And then we'll move on to the discussion of the fractional metals that can be expected in these kind of systems and extension in more rhombohedral graphene systems. So this is the band structure of graphene, whose bandwidth is roughly 20 electron volts, and therefore it is a typical non-correlated system. And its band structure in the low energy sector can be represented by this 2x2 Hamiltonian in the basis of sublattice pseudospins. So this is the pseudospins that we are going to be talking about. And as soon as we add a second layer, the linearly dispersing bands turn into parabolic bands. And when we apply an electric field in the perpendicular direction, it is possible to open up a band gap in the system, therefore changing qualitatively the properties of the electronic structure. A similar situation happens when we move on to 3 layers. So this is the band structure of trilayer graphene, but only when they're stacked in the ABC sequence. This is when they have a rhombohedral stacking. When they have the usual Bernard stacking, you would have a combination of a parabolic and linearly dispersing bands. And the general feature we can expect is that it goes from P to P squared, P cubed. And additionally, we have a winding of the pseudospin spinner in the incline direction whenever we make a cut of the Fermi surface. So the pseudospin arrows wind once when we make a closed loop, closed contour, and it would wind twice in a bilayer system where the chirality is 2. And the same would happen for j = 3, j = 4, so on and so forth. And again, so this is the low energy Hamiltonian representation of rhombohedral multilayer graphene. Here we are representing a 5-layer ABC stacked multilayer graphene, where the pseudospin bases again are the lattices that are at the outer layers of the top and bottom layers. So when we represent the Hamiltonian in these bases, we can have this compact representation in a very convenient manner. And one thing we can observe for its band structure is that its linearly dispersing band becomes parabolic and cubic, and they progressively flatten. Therefore, they progressively become more massive. And so what happens when we consider Coulomb interaction? This is already very old work. So this is a representation of the different phase diagrams that you expect in bilayer graphene. So in fact, there are many, many papers published in this field. I'm just paraphrasing some of all the literature directly relevant to the work being presented. So the y-axis is the carrier density, doping, and the x-axis is the strength of the Coulomb interaction that is represented by this effective fine structure constant. And here in this graph, we see that for single layer graphene, we need alpha to be sufficiently large in order to produce a broken symmetry phase. For n = 2 for bilayer, we get like Coulomb interaction instability for infinitesimally small Coulomb interactions. And that, let's say, that strength of Coulomb interaction increases when we increase the carrier density. So we'll get back to this kind of consideration later. And specifically for bilayer graphene, this is how the pseudospin arrows look like when we add Coulomb interactions. Everything looks the same, except for this region in the middle, near the Dirac point, where instead of winding arrows, we get this kind of dots that represent the pseudospins pointing in the z-axis or pointing in the outer plane axis. And that's, intuitively, we can think the reason for that being all these arrows, they try to align in the same direction due to Coulomb interactions. And due to the quick rotation happening near the K points, so in order to avoid that frustration, they sort of start pointing in the outer plane direction. So that's what what has been named as pseudospin magnetism. So at the mean field level, the kind of ordering of the pseudospins in bilayer graphene is ordering where the charge density sloshes from one layer to another. So spontaneously, you get a ferroelectric material. That's what you would expect in bilayer graphene. And this graph here is the energy breakdown of the different contributions. So this black line is the total energy. It shows that the total energy of the system favors the ferroelectric phase, despite that the Hartree energy or the electrostatic energy contribution goes against that kind of ordering. So this is somewhat surprising, but this was the proposal from a theory viewpoint. And so here, the name of ferromagnetic refers to the ferromagnetism of the pseudospins, but then in the end, we are talking about charge density in one layer going to another. So that's maybe one of the ideas that you have to keep in mind. What happens in bilayer graphene when you add Coulomb interaction? You get ferroelectric solutions in principle. Now the story, so if you do a similar calculation in the lattice, so there are many other details here that I'll probably, I'll highlight only one of the few aspects. So when you open up a band gap in this system, in a bilayer, you have associated a Berry curvature that produces an orbital moment. And because we have 4 copies, 4 flavors in total, we have 2 valleys, K and K prime, and we have spin up and down. And each one of those spin valley flavors can open up a band gap and move the charge to the top or bottom layer. We get a large combination of different ground state that can be expected in this system. And that's what is represented here. Again, ferromagnetic, and antiferromagnetic. Those refer to pseudospin magnetism. And these are all the hysteresis curves as a function of carrier and as a function of electric field. And but again, AF antiferromagnetism means that the charge is balanced. We have equal charging of the top and bottom layer, but then each one of the pseudospins are polarized up and down, such that the charge density cancels exactly. So when we look at this graph on the right-hand side, we expect that the antiferromagnetic phase should be minimum in energy as it is here. This is the blue curve. And so this is showing the total energy as a function of electric field. And we know that when we apply a strong electric field, we should favor the ferromagnetic phase, where all 4 components are pointing in the same layer direction. And in between, one would expect some phase transitions. So, and already a long time ago, in 2011, 2010, Amir Yacobi's group, they showed some non-monotonic behavior of the band gap as a function of the electric field in bilayer graphene. Let's say strictly speaking, is the resistivity, the sheet resistivity decreasing and then increasing again when we apply an electric field. And somehow, roughly speaking, we could associate that behavior with this AF phase undergoing like a complicated phase and then bouncing back when we apply a sufficiently strong electric field. And if you, again, these are like very, very detailed. We made a list of different types of topological phases that can be expected when we distinguish the valleys or the spins or the top-bottom layer pseudospins. So we can, depending on how we polarize these four spin valley components, we can get either, we can decompose the different contributions to the whole conductivity. So this is again the same representation, but then also applicable for rhombohedral multilayer graphene, where these four spin valley flavors, in this case, they are polarized completely to the top layer. And we get the quantum value Hall phase, whereas these three phases are the charge balance configurations. But we, nevertheless, the Hall effect can be completely different depending on how we break the symmetry of the system. So yeah, these are the different topological phases that we can expect in rhombohedrali stacked multilayer graphene, including bilayer graphene. And the interesting development in recent years is that people have started making the system experimentally. So all the work was done mainly for these bilayer graphene systems. But then people can also make ABC trilayers, and nowadays 4 layers, 5 layers, and I've seen up to 6 layers in the literature. And then experimentally, this is an experimental representation. The resistivity shows a big jump when we go to a 4-layer system. It kind of looks like we've trespassed the threshold where the Coulomb interactions start manifesting itself very clearly. And this is a representation of those experiments from Chen Guorui's group in Shanghai Jiao Tong University. And the y-axis is the electric field, and the x-axis is the carrier density. Those red spots represent peaks in the resistivity, showing that they have an insulating-like behavior near the charge neutrality when we have very small electric fields or very large electric fields. So this large electric field regime can be understood from the layer inversion symmetry breaking that we discussed about previously. When we have sufficiently large electric field, we open up a bandgap in the system, and the system becomes naturally insulating. Nevertheless, this peak of resistivity near charge neutrality for small electric fields should be attributed to Coulomb correlation effects. And once again, we can do a similar analysis for these 4-layer systems and compare the different ground states depending on the type of pseudospin polarization, and then expect the crossover of all these different competing phases. And okay, this is just work in progress, just to show that a small spin orbit coupling term of roughly 1 millielectron volts in its prefactor is able to alter the expected ground state in these mean field calculations. Okay, so this was about the Coulomb interaction effects or pseudospin magnetism in rhombohedral multilayer graphene. So this was kind of a preamble to talk about the fractional metals or spin valley polarization that you expect when you carrier dope the system and you break the inverse symmetry of this system. So, rhombohedral multilayer graphene are, again, quite interesting platforms. So here from P1 to P4, we are showing the number of flavors that are being filled when we carrier dope the system. We know that by using a backgate, we can charge the system with electrons or holes. So P1 means that one flavor is being occupied, whereas P2 shows that only 2 flavors are occupied, and P3 and P4, so on and so forth. And again, chronologically, so this was the first experimental paper that was published 3 years ago in Nature, where they are able to distinguish the different types of spin value flavor polarization through compressibility measurements and also through measurements of these magnetic oscillations that are able to count the number of Fermi surfaces that are expected in this system. But again, all this was followed up very quickly by other groups, or even the same group for n equal to 2, 3, 4, and 5 layers in recent years. And okay, so these are the actually the different figures that for 2 layers, 3 layers, 4 layers, and 5 layers. And chronologically, this was first, and then they came up with these bilayers, and then the 5 layers and 4 layers. So it's kind of, the ordering in time is a little different. And all these systems show like quite interesting behaviors on their own. So here I wanted to remind you about, well, one of the physics that were proposed for this kind of system where we have a strong electric field and we carrier dope the system, we get this kind of a rotational symmetry breaking or nematic phase when we occupy a tip of the band edge. And so this is the same representation. When we further carrier dope the system, we restore the nematicity is gone away, but then the spin value flavor polarization persists. And of course, when we keep increasing the density, at some point, it will come to the P4 phase where sort of all these topological properties are gone. And so this kind of behavior, the breaking of the rotational symmetry, well, can be argued in terms of this Fermi ring shape, or understood as some kind of Fermi surface instability or Pomeranchuk instabilities in this multipolar expansion. And already a long time ago, people were talking about momentum space condensation. Well, Heisenberg was attempting to claim that the Coulomb exchange was the reason for the superconductivity already in the 40s, and London was also like picking on that idea to sort of propose this kind of favoring of bunching of states that are close by in momentum space. And now I'm going to discuss the energetics of this spin valley flavor polarization. So these are the comparisons of energies when we fill evenly 2 flavors. And this red curve is the one when we fill only one of the flavors. So like breaking these like time reversal symmetry of the system. So when we have this concave shape, we favor the flavor polarization, whereas when we have this concave, convex concave shape, it goes against the flavor polarization because this straight line stays below the red line. And so this is also associated with the so-called compressibility of the system. And we can do like a breakdown of the energetics, of the kinetic energy, the Hartree energy, the exchange, and the Coulomb correlations within the RPA level, where we calculate all these density response functions. And well, this is a complicated figure, but I just wanted to highlight a few aspects. So this is the Mexican band structure that you expect in rhombohedral multilayer graphene systems. And the behavior of the energetics is different when the filling is below the top of the Mexican hat top, where you have two Fermi surfaces, but then at some point it becomes a Fermi surface and a point, and beyond that point. So that's why, in principle, you get a discontinuity at the moment the Fermi surface becomes a point. And these are the energies. And here we have the second derivative of the energy with respect to density, which is related with these with this compressibility of the system. And here, I just want to show that when you go from the black to red, so the black is without electric field, and the red lines represent the electric field. So you see that the you get very quickly a negative compressibility when as soon as we apply an electric field for sufficiently low electron doping, and that is shown here in this figure on the right. And we could obtain this kind of phase diagram for 2 layers, 3 layers, 4 layers, 5 layers, so on and so forth. So this figure is for a 3-layer system. And here we're showing this figure shows the energy breakdown for this line going from for a finite electric field. And here again, one thing is that we do not see we see a continuous sequence going from 1, 2, 3, 4 flavor polarization, unlike the experiments where we see where they show 1, 2, 4. So talking about the validity of our work, so our work is supposed to work in the limit of very strong electric fields and large densities. And qualitatively, the phase diagrams, the match in the magnitude of the densities and electric fields. Here, for the Coulomb interaction, we're using alpha is equal to 1. That means the dielectric constant is 4. And the scales kind of match the experiment. Nevertheless, we don't know yet why this P3 phase shows up in theory, whereas in experiment it is absent. Okay, so that would be the story for the second part. And finally, I just wanted to tell you a few things about the band structures of rhombohedral multilayer graphene systems when they are interfaced with HBN, when they produce moire bands. So this is an experiment that somehow ignited that work. And this is a representation, again, of resistivity as a function of top gate and back gate, which means that in this diagonal, we have the carrier density, And along this other diagonal, we have the electric field. And again, for the charge neutrality point, applying a very strong electric field opens up a band gap in the system, and therefore it's natural to expect highly resistive phases, either in this corner or in this other corner. But then for other electron densities, like 1/4 or 1/2, in principle, these should be metallic phases, and having a strong electric field shouldn't, in principle, produce these bright peaks. And so these peaks are expected to be Coulomb interaction driven. And the way to explore this was adding these Moiré pattern terms to the continuum model that we had discussed about previously. And when we do that, this is the folded band structure of trilayer graphene. The Moiré potential produces these avoided gaps. Applying an external electric field opens up a band gap at the primary point. It produces this kind of isolated and very narrow bands. And this is the phase diagram of the bandwidth of those narrow bands as a function of twist angle and applied electric field. And we see that for finite twist angle, you would expect like narrow bands, narrower bands than even at zero twist angle. And one can calculate the Chern numbers, the valid Chern numbers of this system. And again, one obtains a like finite valid Chern number, which suggests that it can lead to topological phases when appropriate broken symmetry phases are achieved. And this is the schematic representation of these 4 copies of these nearly flat bands. So this is the Fermi level, where when those 4 levels are occupied, you would expect this kind of quantum valley Hall effect. But as soon as you fill only one of them, or only a small selection of them, you would start getting all these quantum anomalous Hall phases with a finite charge Hall effect. And actually, so this kind of system was measured experimentally. Again, this is a resistivity as a function of density and as a function of magnetic field. They observed a nu equal to 2 phase. And again, so this was a little bit, well, not consistent with the valid Chern number 3 picture that we had calculated at the single particle level. And the explanation in this paper was that the Coulomb interaction somehow would lead to this kind of situation. A single particle explanation of this behavior would be if you add a off-diagonal term with the low energy Hamiltonian, one would sort of break the rotational symmetry of the system and eventually lead to this kind of Chern number equal to 2 phase. So this kind of a proposal. And it would be interesting to observe this with other kinds of probes. And we can extend this kind of analysis for 4 layers, 5 layers. And for this kind of system, we also expect that finite twist angles do not necessarily deteriorate the formation of the flat bands. And in fact, we can achieve narrower bands than in trilayer graphene. And for this purpose, we have carried out some modeling of this band structure of rhombohedral multilayers. So these are the tight binding parameters that we propose, well, based on the local density approximation. And these are transferable parameters. By transferable, we mean that it can be applied for 3, 4, 5 multilayer systems without changing anything else. And when we do this kind of analysis, we see that the valley Chern number of this multilayer system up to 8, they are essentially proportional to the number of layers. It means that we can achieve a pretty high Chern number by just incrementing the number of layers in the system. And so one last thing that I wanted to mention is actually we have proposed these tight binding band parameters of rhombohedral multilayer graphene systems based on LDA calculation, but then one can always improve or try to improve this kind of prescriptions by adding like Coulomb interactions, let's say extended hover-like models following recipes proposed by Agapito Cochiccione. And we can, from ab initio, calculate these kind of parameters. And then in these cases, the expected band gaps of the system are kind of close to, at least for 4 layers, up to four layers, are kind of consistent with the experimental measurements. And these large gaps expected for, okay, we have a variety of experimental results that they're not always agreeing mutually, but at least within this picture, the band structures, so this would be for a tri-layer system. It would not really open up a band gap, and the band gap would start opening from 4 layers onward, at least within this prescription. And okay, and with this, I think I was too concerned about the delays in the previous talk. I think I went a little too fast. And so these are the conclusions of my presentation. And then the energetics of the fractional methods that we can expect in rhombohedral multilayers are closely related with these saddle points, or with the increase of the density of state that you get in the Mexican hat band structure. That's one of the conclusions. And then, in principle, if you want to study this kind of systems, we've proposed like ab initio-based band structures for these kind of systems. And then we can, in principle, explore many new competing phases by changing the experimental conditions. So with this, I think, well, thank you for your attention.
The floor is open for questions. Arindam.
Yes.
This n-layer systems with the Chern number, which is proportional to the number of layers, yes. Is there a limitation eventually? What, can you get 1,000?
Yeah, probably not, but somebody should do that research, I think.
Okay.
Because 8, 9, 10, of course, when you have a rhombohedral graphite, then along the z-axis, you get this kind of spirals of the Fermi surface. You get a very peculiar Fermi surface with holes and pockets. They look like sausages. Mm-hmm. And when does the finite multilayer stack become graphite? That's something I don't exactly know. And maybe the crossover is already at 6 or 7, but I think that research should be done by either experimentalists or theories.
Can I ask one more? Okay. You said Chern number which are all larger than 1. Is there a way to get fractional Chern number in any of those derivatives of either twisting or anything else?
Well, actually, one of the latest big discoveries were these fractional, were channel insulators and the quantum anomalous Hall effects, actually in rhombohedral pentalayer system. So that was, maybe I should have shown that figure. In fact, that's one of the big discoveries, recent discoveries, together with the fractional channel insulator in MOTE2, twisted MOTE2. So, so why not, when you improve the quality of these multilayer systems, you will see also in combination with other substrates. I think it will be quite interesting to explore those regimes.
Thank you for a very nice talk. So for this spin valley polarization states that you were describing, what's the role of the temperature in that case? Like, does it play any role? Would they vanish at some temperature?
Mm-hmm. Yes, in fact, I haven't shown any of those temperature results, but then, yeah, certainly the temperature will smear out all these Coulomb interaction effects. And in fact, all this analysis is done at the mean field level. So then, of course, people that can come up with more sophisticated methods could propose different kinds of truly correlated ground states. I think the story is not finished, in my opinion. And I think yeah, better many-body techniques should be used to study the nature of these phases. And normally the insulating phases, they vanish like, okay, I don't remember the numbers, but then few tenths of Kelvin, they persist up to those. Yeah.
Thank you.
More questions?
Okay.
You know which phase? You know which phase I mean?
Yeah. Well, I showed that slide, but then in fact that was work in progress, and also, again, highly sensitive to. Let me see. Sorry for. Highly sensitive to different model parameterization. Okay, this is a spin-orbit coupling model that was proposed in one of these Yaroslav Fabian's work. And for bilayers, I mean, for ground state, you will get this Fi phase, ferroelectric phase, which is quantum anomalous Hall, and spin polarized, let's say the all phase, the interesting phase. Again, I think this, at least for the bilayers, this prediction needs to be taken with some care, because the mean field gap is actually quite large when in experiments they are almost negligibly small.
Is this a charge neutrality point?
Yeah, this is a charge neutrality point. So this was just to illustrate that how sensitive the different solutions were to a very, very small introduction of the spin-orbit coupling term. So then, again, we might expect yeah, different substrate like tungsten, like selenide with different twist angle would completely change the picture. And still, it will be interesting to see what happens in experiments.
Thank you.
More questions?
How you decide the screening constant?
Sorry?
How do you decide the screening?
The epsilon here.
Yeah.
Well, for graphite, we normally, and diamond, I mean, all these carbon materials, I think we normally expect a value of between 5 and 6, or 4, 5, 6. Actually, people, I think this can be also calculated ab initio, depending on which axis. We've just taken a common value in the literature. So this is kind of an ad hoc choice of a value that is not too far from what has been used in the literature for graphite. So normally it's 5, roughly. But then for twisted multilayer system, people take 10, 20, or 30 to effectively account for screening effects that you get when you have more electrons near the Fermi surface. Because otherwise you would blow up the system. So this choice is kind of taken ad hoc from graphite literature. But this can be refined also, depending on which direction. And, yeah.
So as you change the layer number, the screening constant also will change, right?
Yes, strictly speaking, it should, I think, because strictly speaking, it should. Now, how much it changes, I don't know yet, because that maybe should be calculated ab initio. And also it could be that the Coulomb interaction effects are happening mostly at the surfaces. So maybe things might not change too much. So I don't have a clear answer to this at this moment, but probably it doesn't change too much, but it needs to be verified.
Yeah, one last. So
Last one.
yeah. So I mean, in experiment they put the electric field, right? Mm-hmm. But in theory calculation we use like interlayer potential. We don't put electric field directly, right? So how you like convert this electric field to interlayer potential? Do you just divide by the thickness?
No, this is it's a self-consistent calculation where you sort of, well, all these were done at the Hartree-Fock level, where the direct term accounts for the charge screening and the exchange term also. They are all considering the same footing. Yeah, so the electric field is just the interlayer potential change between layers.
Any more questions? Okay, in that case, thank you very much, Jeil, Jung.